The creek bottom moves. 2 billion shells settling into silence. Harris Creek had been ecologically dead for decades. Diseases, pollution, a century of overharvesting had stripped every living reef from the mud. Then, in 2011, they seeded 350 acres of that dead floor with juvenile oysters. No one projected what came back. What grew beneath that surface became the largest tributary reef restoration ever recorded on Earth. For decades, nothing anchored the bottom of Harris Creek. The water moved, grey and indifferent, above a mud floor stripped of every reef structure it had ever built. No shell, no grip, no filter pulling the water clear. Oysters had once built the Chesapeake's underwater architecture across thousands of acres of reef. A century of overharvesting, then 2 back-to-back diseases reduced the bay's oyster population to roughly 1% of its historical level. Harris Creek held almost nothing. Dermo and MSX, 2 parasitic diseases, had moved through the bay's reefs like a slow fire since the 1950s. By the time restoration programs began designing intervention, the living reef in Harris Creek was functionally gone. Engineered solutions had been tried: artificial substrate, constructed breakwaters, water quality interventions costing millions of dollars per creek mile. The water did not clear. The reef did not return. Each failure left the same blank mud. In 2011, the Chesapeake Bay Foundation, NOAA, and the state of Maryland made a different calculation. They seeded juvenile oysters, not tens of thousands, not millions, across 350 acres of creek bottom. The number placed into that dead water was 2 billion. Not a metaphor for scale, a documented, staggered deployment across multiple seasons, organism by organism, dropped into substrate that had not held a living reef in living memory. Each juvenile oyster arrived at the bottom as a filter. A single adult oyster clears roughly 50 gallons of water in a day. Stack 2 billion of them across 350 acres of creek floor, and the arithmetic of recovery becomes something you can measure from a boat. Within a few years, program biologists began recording elevated reef structure on sonar transects. The creek floor had risen. Not sediment, hard biogenic reef, built by the animals themselves, reading as solid terrain on the survey equipment. No engineer had specified that outcome. Every engineered intervention before 2011 had spent more per acre than the oyster program and left nothing standing. The animals rebuilt terrain that concrete and steel could not hold. The reef that came back in Harris Creek is now the largest documented tributary reef restoration ever recorded. What the program's biologists found beneath the surface, season after season, was a structure that should not have been possible in a waterway this chemically compromised, and the mechanism that allowed it to survive the first winter is the part no projection had anticipated. The oysters did not wait. They simply began, and what they built next rewrote every expectation the program had written for them. Most people crossing the bridge above Harris Creek saw the surface and assumed that was enough. That glint of tidal grey looked like a functioning estuary. It was not. Monitoring divers running transects along the channel floor found stretches where they could find the entire length of a survey line without contacting a single live shell. Not sparse, not thinned, gone. Across the broader Chesapeake system, populations had declined to less than 1% of their estimated historical abundance. That number does not describe scarcity. It describes functional extinction at an ecosystem scale. The geographic record reads like a ledger of erasure, zone by zone. In the upper shallows, where reefs once stood tall enough to breach the surface at low tide, the substrate had gone completely flat. No vertical relief, no brood stock, no surface for larvae to settle on. Across the mid-channel, submerged grass meadows had retreated from depths they had held for centuries. Along the lower mouth, where tidal exchange runs hardest, unanchored sediment moved freely through the column. That sediment movement is not a cosmetic problem. Fine particles suspended in the column absorb light before it reaches the bottom. Grasses cannot photosynthesize. Without grasses, the fish and blue crabs that sheltered inside them had nowhere to go. What a functioning reef structure actually does is architectural. The shell matrix raises the living layer off the smothering silt. It creates a surface, a current shadow, and a recruitment platform, three distinct physical services stacked inside one living formation. Harris Creek had lost all three. The formation was gone, and with it the entire cascade of physical consequences that formation produces. That is the part the surface never shows you. A drain and an estuary can look identical from a bridge. The programme's biologists documented that the collapse had persisted for long enough that an entire generation of larvae had cycled through the system and found nothing to attach to. Season after season, for roughly 3 decades, the substrate had been empty longer than most restoration ecologists had been watching it. Here is the number that should not close cleanly. The programme seeded 350 acres of that sterile substrate, and the early post-planting density counts came back higher than any pre-project model had projected for year 5. The mechanism that allowed newly planted material to survive the first thermal stress event, the first summer oxygen crash, was not accounted for in any of the baseline projections. What the programme found in year 2 of monitoring turned the standard recovery timeline inside out. That finding is what the next set of field records document, and it starts with a single season's dissolved oxygen reading that nobody on the survey team expected to see. That dissolved oxygen reading sat in the field logs for 2 weeks before anyone published a comment on it. The number was higher than it had any right to be. Mid-creek, mid-summer, in water that had collapsed to near zero in every prior August on record. To understand why that reading mattered, you have to go back through 3 decades of effort that preceded it. Hatchery trucks, harvest bans, water quality targets. Each one arrived with a defensible rationale and left behind monitoring data that showed no measurable reef recovery at creek-wide scale. A single adult oyster filters up to 50 gallons of water daily. No engineered clarification system deployed in the Bay watershed has matched that rate at creek scale, not without continuous power draw and maintenance cycles that exceed the filter's own output value. The critics were not wrong to raise the questions they raised. Seeding 350 acres at high-density risks, concentrating harvest pressure before a reef can lock in its own architecture. The uncertainty was real. The debate inside the industry ran for years before the first barge moved. The objections stacked up along 3 lines: ecological risk at that planting density, premature harvest pressure before the reef could self-sustain, and a cost-to-uncertainty ratio that made the project look like a gamble. The oysters did not wait for the debate to resolve. The moment they touched bottom in Harris Creek, they began filtering. Not as a response to management targets, not as a reaction to water quality regulations. As biology, the same reflex a spat uses 48 hours after it sets. Within 2 years of the initial planting, the field team's transect data showed live reef cover across acreage that no prior restoration effort in the watershed had approached. Dozens of benthic species, juvenile blue crabs, grass shrimp, small finfish, were logged on structure that had been flat for a generation. Here is what the earlier programs never replicated. The reef itself changes the physics of the water column above it. Vertical relief slows current. Slowed, current drops, suspended sediment. Dropped sediment lets light reach the bottom. Light reaching the bottom is where submerged grass returns. The pre-restoration baseline logged near 0 live reef acres across the monitored reach. That gap, 0 against 350, is not a number from a model. It is the measurement the survey divers brought back up. Every dollar spent before 2011 carried a real cost. But the cost that never appeared in any budget line was the cubic feet of water that went unfiltered each day the reef stayed flat, the grass that stayed dark, the larvae that arrived and found no vertical structure to settle on and drifted out with the tide. What the monitoring logs show next is the part that changes how you read every prior management decision in the bay's history. The reef did not just filter water, it altered the thermal profile of the water column above it. And that alteration is what the oxygen data from year 3 cannot yet explain. The thermal shift was the first signal. Not a dramatic reading, a quiet, persistent difference in temperature between the column above the shell and the open channel beside it. The oysters were drawing heat out of suspension, along with everything else, and the instruments caught it 3 weeks before any biologist thought to look. Each individual animal was pulling roughly 50 gallons through its body daily, not storing it, not transforming it, just passing it through and dropping what it could not use to the floor as dense, bound pellets. Multiply that by 2 billion and the arithmetic becomes physical. You can see it in the sediment cores. The material that once floated simply stopped floating. As suspended particles settled, the turbidity dropped. Sunlight reached the creek floor at depths it had been blocked from for decades. And something that had been waiting for exactly that light began to move. Submerged aquatic vegetation needs a minimum light threshold to photosynthesize, and for decades the turbidity had held the canopy just below it. Within 2 seasons of the seeding, the field team's transect surveys documented grass beds returning across monitored margins, not planted, not seeded, returned. Those grass beds are not decoration, they are the nursery. Blue crab larvae settle into them, juvenile striped base shelter inside them. The same meadow structure that disappeared when the light went dark quietly reappeared. And the animals that belong in it followed the physics, not a management plan. The shell surface itself reorganized the habitat in 3 dimensions. Ridges of accumulated shell rose above the flat substrate, creating crevice structure that a scoured mud bottom simply cannot offer. Toadfish moved into those gaps, small eels followed. Spawning blue crabs found vertical structure to anchor against. The kind of architecture that takes natural reefs centuries to build without intervention. This is the part that made me stop and reread the field notes. The bird surveys. Within a handful of seasons, monitoring teams recorded wading species using the shallows in numbers Harris Creek had not supported in any prior survey log. The birds did not know a restoration had happened. They knew the fish were back. The sequence was not designed, it was physical. Particles settled, then light returned, then grass grew, then invertebrates colonized, then fish arrived, then predators followed. None of these arrivals required a separate program, a separate budget, or a separate decision. 350 acres of shell substrate had become functional habitat for species nobody catalogued in the original permit application. The invertebrate communities rebuilding in the grass roots, the worms, the small crustaceans, the benthic fauna, represent the nutritional foundation for every commercially significant species the bay has ever produced. What no monitoring protocol had anticipated was the speed. A reef that ecologists estimated would take a generation to establish functional complexity had begun delivering measurable ecological services inside the first 3 years. The mechanism behind that compression, why the sequence moved so fast, is exactly what the program's biologists are now trying to isolate in the bay's other tributaries. The survey divers were not expecting what they found at the coordinates they had logged since the first planting. Recruitment had outpaced every projection in the reaches where tidal flow funneled larval supply, and the reef had grown vertically in ways the models simply had not drawn. In the densest clusters, the competition for vertical space drove mortality rates that briefly alarmed the monitoring crews. What stabilized the structure was the reef doing what historical reefs do, self-thinning into layered architecture, the weaker animals dying and becoming the platform the survivors grow on. Across the 350 acres of restored bottom, the collective filtration capacity of 2 billion animals working simultaneously had been modelled conservatively, and the bay's own water column told the monitoring teams the models had undershot. Water clarity gains were real, but they were not uniform. A single storm mobilises sediment from across the entire watershed, thousands of acres draining at once. The reef can only process what the tidal cycle carries to its perimeter. It cannot reach upstream and stop the land from moving. In the fastest recovering reaches, turbidity dropped measurably within the first growing period. In sections exposed to heavier storm loads, clarity remained erratic. The same reef, delivering 2 entirely different results within a few hundred meters of each other. And then there is the complication nobody in the program considered a problem until they began looking at it closely. Blue crabs moved into the reef crevices in documented numbers, exactly as the program's biologists had hoped. A reef that holds blue crabs is a reef that is working. Blue crabs are also predators of juvenile oysters. The reef built the community that will now exert permanent pressure on its own next generation. Every spawning season for as long as the reef stands, that is not a failure. That is exactly what a functioning bay ecosystem looks like. It has never been simple. What the models had drawn was a linear progression. Seed, recruit, filter, recover. What the bay delivered was a web. Recruitment concentrating in high-flow corridors, self-thinning producing the layered structure, filtration outpacing projections, and a new predator community closing the loop. A reef large enough to restructure a creek's hydrology is also large enough to change the predator community living inside it. And a system healthy enough to hold predators is a system that will never again be easy to manage, because it is alive. Alive systems do not hold still for models. The program's biologists are now carrying what they learned here into the bay's other tributaries, each one with its own flow patterns, its own sediment loads, its own predator populations. What the models get right in one waterway, they may underestimate in the next. Each tributary the restoration team moves into carries a different history of loss, but the physics underneath is identical. Remove the pressure, return the substrate, and biology moves toward complexity the way water moves toward the sea. Harris Creek holds that proof in its sediment column. Core samples pulled from the creek bottom show a layer of compacted shell and organic material that predates European settlement, a biological archive of what this system once was, and in 350 acres of restored bottom, is becoming again. The submerged aquatic vegetation tells the same story differently. Grass beds that had effectively disappeared from large sections of the creek have begun recolonizing within the reef's shadow, where sediment suspension has dropped enough for light to reach the bottom again. Surveys document grasses returning to depths where none had been recorded for decades. Grass beds are not decoration. Each acre of healthy seagrass sequesters carbon, stabilizes sediment, and provides nursery habitat for juvenile fish that no oyster alone can shelter. The creek is not recovering along a single axis. It is recovering along every axis simultaneously, which is what a system does when it is no longer fighting to survive. And here is the number that the field team did not forecast. The returning grass beds are now trapping fine sediment at the creek margin, building elevation in areas where the bank had been eroding for a generation. The reef restructured the column. The grasses are now rebuilding the edge. Neither was in the original restoration plan. That is where the system surprises you. Plant 2 billion animals into a dead creek, and the creek does not simply filter. It rebuilds sequentially, structurally, across every trophic level, in an order that no single model fully anticipated. The surprise is not the scale. The surprise is how many separate processes switched back on at once. What remains genuinely open is the long-term nitrogen budget. The reef removes nitrogen through denitrification in its shell matrix, a documented process, but the watershed above the creek still delivers nitrogen loads that no restored reef, however large, can fully offset on its own. Drop your region, and one species you have personally watched disappear from your area in your lifetime, a fish, a bird, an insect that used to crowd the shoreline on summer evenings and then simply stopped coming. Leave it in the comments, because what happened to it matters, and the record of what was lost is part of the evidence for what can return. And yes or no in the comments. Have you ever seen something come back that you were certain was gone for good? Because if the answer is yes, I want to hear that story. Share this with someone who still believes the damage is permanent, because the evidence says otherwise. The creek does not negotiate. It simply continues. Next, wolves reintroduced to Yellowstone in 1995 reshaped the courses of rivers they never touched, a cascade so complete that the rivers themselves moved. The US Fish and Wildlife Service resisted full delisting for years after the population had stabilized, citing livestock depredation data from a single state. And during that delay, pack structures collapsed in exactly the territories where riverbank vegetation recovered slowest. What remains unresolved is whether a cascade that deep can hold in a landscape where the apex predator's range overlaps continuously with working ranches. Because the ecology says yes, and the land tenure map says something more complicated.